Calculus and candy. Calculus, a particular dialect of the language of the universe developed in the 17th century by Sir Isaac Newton and Gottfried Leibniz. This branch of mathematics is built around approximation and divides into two smaller branches: differential calculus, the study of rates of change and their correlation with linear graphs, and integral calculus, the study of quantities and areas between and under curves. To start, we're going to be looking at integral calculus. The idea of integral calculus is making an approximation with the highest accuracy possible, using the method of dividing the units of measurement infinitely, or off into infinity, however you want to put it. Wait, you didn't quite catch that? Okay, let's put it this way. Let's say you have a curve and you want to know, or rather guess, exactly what the area under the curve is. For the purpose of this video, our units of measurement will be Oreos, chocolate peppermint truffles, and gummy worms. Knowing that the cross-sectional area of an Oreo is roughly 15.2 square centimeters, let's see how many Oreos we can fit under the curve. Great! If we multiply that by 63.7 square centimeters, we have this, our guess of the area under the curve. But look at all this empty space that's been left unmeasured. So let's divide that unit of measurement to get a more accurate approximation. Now, our unit of measurement is a chocolate peppermint truffle with a cross-sectional area of roughly 5.3 square centimeters. After removing the Oreos, we can fit this many chocolate truffles under the curve, and now we have much less empty space left unmeasured, making our area approximation of this much more accurate than that. But we can still do better. Let's replace our chocolates with our next unit of measurement, gummy worm, each of which has a cross-sectional area of about 3.5 square centimeters. Now, after fitting this many gummy worms under the curve, our new approximation of the area under it is this, which is even closer than the last. This can continue for as long as we want it to. We can choose nerds, for our next unit, then pop rocks, then pixie dust, and keep going, forever. The closer we get to infinity, the closer our approximation is to the actual area below the curve. Now for differential calculus, which is centered around derivatives, rates of change, and their realization on a linear graph. Okay, so that sounds a bit intimidating. But let's try this. Imagine Amanda is having her 10th birthday party, and before the party starts, she puts out a very big plate of Oreos. Before any guests arrive, Amanda eats one Oreo every 10 minutes. After the first guest arrives, Amanda eats 2 Oreos every 10 minutes, as does her guest, because they both want to get the cookies before the other kid does. Every 10 minutes, another guest arrives, and with each new guest, Amanda eats one more Oreo per 10 minutes, so that after her 10th guest's arrival, she, along with all the other kids, eat 10 Oreos every 10 minutes. Make sense? Good. Differential calculus takes all of those different factors and functions and solves problems with them. It studies the effect that these factors and functions have on each other. As far as graphs go, these factors can be formed into functions with which to form graphs that show how quickly the rate of Amanda's Oreo eating increased.
With differential calculus, we can figure out how quickly the rate of consumption increased with the arrival of each new guest.
In conclusion, calculus is a very special branch of mathematics, loved by those who know it because of its power to accomplish things no other branch of mathematics can, and its elegance and ability to accomplish said things in such a compact way. Like all other types of math, it is just an expression of everyday occurrences in numbers, and is therefore intuitive to each and every one of us. It is but one of the dialects of the language our universe is written in, and should be treated, loved, and celebrated as such.